Hello everyone, my name is Brian Dosono and I'm a second year PhD student at Syracuse University. This is actually my first ICSE conference and I'm really excited to be here with this Chase group as well. And I'm presenting on behalf of Andrew Ko, who is a professor at the University of Washington Information School, and as well as Niraja Durasetti. And the work that I'm presenting today is work that we've been working 2 summers ago in 2012 when I was still an undergraduate at the University of Washington. And we were just really interested in learning how the past 30 years has really affected or has really transformed the ways software problems are reported in society. All right, so in this paper, we begin to understand this question at the macro scale, investigating the trends in software problems and the consequences by mining archives of failure. Perhaps the most extensive archive of software problems and their consequences is news archives. News is probably the largest recorded acute effects of software failure in society, and through both quantitative and qualitative methods, we investigate the problems reported, the consequences they've had on people and society, and how the consequences reported in the news have changed over the past 30 years. So we selected a random sample of search terms for each of these terms to assess their viability, randomly selecting one article per quarter per database per term from 1980 to 2012. And for a total of 260 articles per term, and then we analyze each article for whether it referred to a software problem or some other type of problem. And we gained the most of our text data from ProQuest, LexisNexis, and Factiva, which are 3 main news sources or databases for news. And these included 93 out of the most 100 circulated newspapers in the United States. And for this project, we focus on news that cover the English language because that's the language that all 3 of the collaborators shared in terms of coding this for content analysis. And so for those search terms, we analyzed an article for whether it referred to a software problem or some other type of problem. And out of those terms, bug, defect, error, fault, flaw, malfunction, glitch, mistake, glitch was the one that was most linked to software problems. So only 11% of the articles with the word bug and 9% of the articles with the word malfunction referred to software. Across the sources we sampled, these types of terms typically either refer to insects, illnesses, and mechanical failures. And for that reason, we decided to focus only on articles with the word glitch, as you can see with the resounding majority of articles involving software problems. And so for this article, we developed a new So we developed an algorithm that converted each article's words into a vector of term frequency, inverse document frequency, or TF-IDF scores, and then iterated through all articles in order of publication date, comparing each article to all subsequent articles published within a 7-day window. If the cosine similarity of any 2 articles' TF-IDF term vector was of 0.25 or greater, which represents a modest similarity, then an edge was created between 2 articles, creating a graph of related articles. And when the similar article was found, the comparison window was then set to 7 days ahead of the date of the new relevant article. This allowed articles to be linked across weeks, months, and years as long as one similar article was published within a week. After comparisons for articles were complete for a day, all disjoint graph components of the article, whose last dated article was no more than 7 days before the current date, were removed from the graph and treated as a separate story cluster. And we chose 7 days in this algorithm because of the weekly news cycle. And the application of this algorithm grouped the nearly 380,000 articles into 58,000 story clusters. And throughout this paper, we refer to an article as a single news report from a single news organization, whereas a story refers to the set of articles identified by our clustering algorithm as reporting on the same software problem. To assess the accuracy of clustering, the authors independently read all articles in a random sample of 550 story clusters spanning 6,900 articles, judging each article as either relevant to the cluster or off-topic. So again, that was a rationale for us to choose the English language as all three of our coders are very familiar with that. We measure the attention a story was given by the press by computing its normalized article count, which was the number of articles per story cluster, excluding duplicates published in different sources, divided by the number of news sources that were available in the news databases in the year the story was published. This measured how many news organizations committed effort to reporting on the story, which controlled for the confounding factor of full text availability over time. And to measure the geographical location from which a story was reported, we assigned a world region, country, and if it was in the United States, a state, to each news source that appeared more than 5 times in our dataset. All other aspects of stories were qualitative measurements which we obtained by coding a sample of story clusters and their articles using content analysis methods. Our sample included a subset of the 58,000 story clusters with 6 or more articles and a random sample of stories with fewer articles to focus our analysis on the stories that received the most attention from the press. Reading these articles spanned about 1,000 in-person reading hours across 2 months. So it was a lot of reading, but we were quite acquainted with the type of news that was reported. This table shows the variables that we coded, and to assess the reliability of each variable in this table, the authors iteratively and redundantly coded random samples of 100 stories, each time computing Krippendorf's alpha for each variable and discussing disagreements. After 3 rounds of redundant coding, which covered 5% of all story clusters, we finally reached satisfactory agreement on all variables. The authors then split the sample into 3 sets and coded each story cluster independently, reading each article in a cluster. For each cluster with more than 100 articles, we read a random sample of at least 10% of the stories to identify the dominant story topic. Alright, while the notable stories varied greatly in their consequences, the top 100 stories receiving the most press were quite homogeneous. The biggest story by far was the Y2K Millennium Defects. Another 13 stories covered fears and consequences of problems with e-voting software from 1998 to 2008. Tallies were delayed and incorrect, machines froze, digital voter registration records were missing names, and votes were lost. This figure shows the number of stories reported per month separated by region. As the plot shows, there are a few problems with reporting in the 1980s with a rapid rise in the number of stories approaching the year 2000. After the year 2000, however, the frequency of reporting appears to have slowly declined overall. In interpreting these trends, it's important to remember that declines in stories in North America may represent declines in U.S. journalism budgets, as opposed to declines in software problem frequency. Alright, so I'll be, in the next couple of slides, just going over the types of variables that we coded and the results for each one. So for first slide, death was rare. Among our coded samples, 47 reported 1 or more deaths related to software. And extrapolating this, the nearly 35,000 stories in our data, as shown in the top figure above, about 400 stories over 32 years were likely reported deaths, and a third of reported deaths were due to collisions in planes and cars, with most plane crashes accounting for most death counts above 50. On land, transit lines and railroads that use the same signaling system have repeatedly failed to detect trains traveling the wrong way. And Toyota in 2010 recalled its hybrid Prius after discovering a design flaw that recovered a software change to fix the anti-lock brake system. And the LA Times reported in March 2010 that 102 people had died from this and other problems with sudden acceleration. In the air, plane crashes stem from pilots receiving faulty readings on cockpit screens, engines and thrusters being reversed mid-flight, and air traffic controllers guiding dangerous landings. Injury was also rare. In our sample, 39 stories reported physical harm. Extrapolating this rate to the nearly 35,000 stories, the number of injured since 1980 is likely about 12,500. Half of the stories reported injuries sustained on boats and ships because of bumps and tilts. In 1997, autopilot problems led a double-decker tourist sightseeing boat to ram into a bridge on the Seine River in Paris, injuring 28 people. Other stories reported injuries in entertainment, health, and manufacturing. On Broadway, a Spider-Man stunt actor was injured after plunging 30 feet due to a computer-controlled harness failure. And in 2008, a big television screen at the Piccadilly Gardens fan zone failed to show a highly anticipated football game, which led to thousands of fans violently rioting against the police, leading to injuries from both parties. Threats to food and shelter were less common in death than physical harm, appearing in only 28 of our quoted stories in our sample. And if we extrapolate this to our 35,000 stories, the number of people reported to have lost access to food and or shelter since 1980 is likely to be about 80 million. A third of stories involved problems that resulted in a delay of government aid to vulnerable populations. Some involved welfare recipients that qualified for food stamps, and students waiting for financial aid that was incorrectly denied or backlogged. 5 stories reported on faulty natural disaster detection systems, including overlooked tornado warnings, missed wildfire notification dispatches, and 911 emergency calls that did not reach an operator. Threats to basic needs were related to regions, with basic need losses overrepresented in the United States. The loss of money, data, and material goods was much more common, reported in 498 of our coded stories, and therefore about 4,400 stories over the next 32 years. About 20% of our stories reported data loss, often emails, court documents, or data that NASA probes failed to transmit. Another 20% of stories were about companies losing revenue because customers had problems with the company's software. The remaining bulk of property losses included incorrect charges that were never reimbursed, regulatory fines due to software defects, stock market loss, and security breaches. While it was difficult to quantify the lost data in physical goods, we were able to quantify lost money, as many articles explicitly reported it. Of a random sample of 100 stories, 28 reported an amount lost due to their software problem, and we converted all these amounts to US dollars using the average exchange rate for the month the story was published. As seen in the top figure, the median loss ranges from around 7.7 million. Delay was the most common consequence, as mentioned in 40% of our articles in our sample. The most common were outages in government services, forcing people to wait days. Software delays were common and typically reported on widely publicized projects, such as new government websites or utility services. Other common types of delays occurred due to outages in stock market trading, banks and ATMs, and flights, voting in elections, NASA launches, phone services, public transportation, and public websites. The shortest delays concerned emergency responses to fires, injuries, and other time-critical services, where a few minutes of delay was a matter of life and death. Several plausible causes could underlie the observed news reporting trends. One instance may be the increased experience with software and how it fails amongst common public expectations within the last 3 decades, making failures less surprising and less newsworthy. A related cause could be that most software problems are becoming harder to observe. Most of the stories in our data are based on press releases or investigations of public organizations. Software failures could be more common within private organizations, but they're simply not reported. It could also be that people pay more attention to the public sector due to a distrust that the public organizations can provide a reliable service. This interpretation aligns with our finding that developing regions of the world where governments are believed to be less reliable report a greater number of software failures in the public sector. Regardless of the underlying causes, our research suggests new directions for software engineering practice. People are highly reliant on software as the only solution, but software should be used in supplement to legacy process systems rather than as a cure-all for all problems. For example, many airports have many alternative processes such as manual check-ins, transporting baggage by hand, etc., to keep operating in the event of software failures. Software design practices should consider the potential for failure in all parts of a system's functionality. The design of a near-perfect software system can lead to breakdowns in human-computer communication, making it hard to detect and fix errors before they escalate. One solution would be to adapt frameworks on universal human needs into a software inspection checklist. And this checklist could focus on the data computed by the software and the decisions it makes and helps review potential for delay, loss, or other human risks. It's impossible to predict all circumstances in which software will run. Delay and property loss were often caused due to the time it takes to support teams to detect, diagnose, and correct an error, rather than the software failure itself. Software should be designed with the recovery process in mind. Current software lacks a middle ground between working and not working, tools to quickly isolate and identify causes for failure, or highly informative error messages to speed the recovery process. Future software should be designed taking these factors into consideration. We sought to understand the consequences of software problems on society and how they're changing over time. And our results indicate a dramatic fluctuation in the seriousness of these consequences, but the majority of consequences were brief and inconvenient, such as delay or property loss. While the most severe consequences are becoming increasingly common, they are relatively rare compared to other risks to humanity. And our results call for a clear definition of how software is correct in software engineering research and beckons practices to educate end users that software is in fact fallible. Thank you for being a gracious audience. Are there any questions?
Yes.
Yes.
I have a recommendation for you.
Yeah.
You said you're in second year of PhD.
Yeah. Yeah.
You will have time to collect data from the Obamacare registration disaster.
Yeah. Yeah.
And that, because this is something that will come up when you defend your thesis.
That's actually a good point. Yeah, especially with the outcry of the Obamacare. I don't think there's a lot of literature on Obamacare that web release yet, but that's something to look into. I really appreciate that insight.
Did you identify the sources of problems for this? I mean, like, what are the main problems? Did you categorize the problems? There are problems in software that are causing, this news.
Oh, so the reporting for this, we coded problems based on different areas in Maslow's hierarchy, and all of our insight and all of our readings come from journalists' account of software. So we didn't code problems from the engineer's point of view. We coded problems from the journalist's point of view, and seeing how journalists document software practices over time. So we don't have the granular data to see where the errors occurred, but we do have a sense of how they're reported in the news. Thank you.
Okay, I think we're at the end of question time for this first paper, so thank you very much.
Thank you so much. Thank you.